So in this video, I will answer a few questions about the gradient vector and its application through a few examples. So the first example is find the parametric equation of the tangent line to the curve of intersection. So the tangent line to the curve of intersection of the paraboloid z is equal to x squared plus y squared, and the ellipsoid 4x squared plus y squared plus z squared is equal to 9. Okay, so in order to get a better understanding of what is going on here, let us just look at this situation. Okay, so again, you can write it down in your notes. Z is equal to x squared plus y squared, the paraboloid, and the ellipsoid 4x squared plus y squared plus z squared is equal to 9. Okay, so let's see what's going on. So the paraboloid is given by this graph right here. Okay, so it's not a graph, it's a surface, right? And there is the point A right here, belongs to the paraboloid, but also it belongs to the ellipsoid 4x squared plus y squared plus z squared is equal to 9. Okay, so this is the point P that obviously belongs to the curve of intersection. Now the curve of intersection, it's right here only. There is a curve of intersection, okay? And what we want to do is find the tangent line. So we want to find this equation here, the equation of the tangent line that touches the curve of intersection of these two surfaces. Okay, so how are we going to do that? So let us define first a function capital F of x, y, and z, okay, that is going to be equal to x squared plus y squared plus z is equal to 0. And similarly, let us define a function capital G, x, y, and z, which is equal to this equation right here, 4x squared plus y squared plus z squared is equal to 9. Okay, so these are going to be, okay, this is nothing, we just brought z on this side and we defined these surfaces, right? Level surfaces. Okay, so let's go back to the, let's go back here. Okay, and let us see what will happen. Let's just concentrate on the paraboloid right here. Okay, this tangent line, okay, it's a tangent line to the paraboloid also, not because the curve of intersection belongs to the paraboloid. This tangent line is a tangent line to the paraboloid, which means it lies on the tangent plane right here. So this is the tangent plane to the paraboloid, right? And then the equation of the line that we're looking for, obviously the line belongs to that plane. Okay, what do we know about this plane? We know its normal vector, because as we said in class, the gradient vector is the normal vector to the level surface, right? Well, we can evaluate that. We can evaluate that gradient vector from here. Grad f or gradient f is just the vector consisted of the partial derivatives of of this function. So partial f partial x is 2x, right? Derivative with respect to x, these are treated as constants. By the same logic, 2y and z, okay? Evaluated at the point negative 1, 1, 2, we get the vector negative 2, 2, 2, right? So that vector is right here. That's gradient f. As you can see, it's orthogonal. It's orthogonal to the tangent plane because this line belongs to the tangent plane. That means that this vector, gradient vector, is orthogonal to the tangent line. At the same time, the curve of intersection belongs to the ellipsoid, right? Which means that the tangent line is going to be part of the tangent plane of the ellipsoid at the point A. So right here, this is the tangent plane to the ellipsoid at the point negative 1, 1, 2, okay? Obviously, the line whose equation we're looking for belongs to the tangent plane, okay? And what do we know? We know the normal vector to this tangent plane, which is nothing else but the gradient vector evaluated at that point. So let's find the gradient vector. From here, gradient g is just equal to 8x, right? Partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, evaluated at the given point gives us the normal vector negative 8, 2, 4, okay? Okay, so that gradient vector is this one right here, gradient g, okay? And this vector, as you can see, being orthogonal to the plane means what? It means that it is orthogonal to the tangent line that is part of the plane that we're talking about. So what do we have? We have we have two vectors given by the gradients, right here. We have two vectors given by the gradients, okay? And a line whose equation that we are looking for, that it's orthogonal to both of them in 3 dimensions, right? So I'm looking for this line that passes through the point P, or A given here, right? So I know a line on the point, and what do I need else? I need a vector parallel to it. I need a direction. Well, if this line is orthogonal to gradient g and gradient f, how am I going to find a vector orthogonal to both of these vectors? Well, from linear algebra, we're going to find that by what? By finding the cross product of gradient g and gradient f. So why don't we simply do that? So gradient f at the point negative 1, 1, 2, cross product gradient g at the point negative 1, 1, 2 is equal to I j k. Gradient f was negative 2, 2, 2. Gradient g was negative 8, 2, 4, right? And this is going to be equal, how much? 8 minus 4, that's 4, right? Negative 8 plus 16 is 8, with negative in front, negative 8. And this one here is negative 2 times negative 2 is negative 2 times negative 2 is negative 4 plus, sorry, negative 4 plus 16 is 12. Okay. Okay. So this is a vector, okay, that is orthogonal to both gradient f and gradient g, which gives us what? Which gives us the direction of the line that we are looking for, okay, which is the tangent line to the curve of intersection of these two planes. Okay, so if we find the cross product of these two vectors, grad f and grad g, then we're going to find this vector right here. Okay, and once having a directional vector and the point, you can just write down the parametric equation. So x is x naught plus vt, y is equal to y naught plus vt, and z is equal to z naught plus vt, which means that x is equal to, the point is negative 1, y is equal to 1, z is equal to 2, plus 4t minus 8t plus 12t. Okay, and just as it always happens, I found a mistake, and of course it's the easiest mistake that, that I can do. I found a mistake in gradient f. Why? Because partial f partial z is not z, but 1. So this is here 1. So let me correct that very fast. This is 1, so 1. So that means that this vector is a negative 2 to 1. The second one is 8x, 2y, 2z. Okay, so negative 2, 2, and 1. So the first component of the cross product is going to be 8 minus 2. And another mistake, okay? When I'm bringing z to this side of the equation becomes negative z. I'm so sorry. So negative 1. So 8 minus minus 2 is 10. Okay. Negative 8 minus, how much is this? Negative 8 minus 8 is minus 16 with negative in front, plus 16. And the last component doesn't depend on this mistake that I did. So the only difference is here. So this is going to be the point negative 1 plus 10t. So plus 10t. The point 1 plus 16t. So plus 16t. Okay. And then z is 2 plus 12 plus 12t. Okay, so let's move on to the next example. Very similar one. Consider the level surface f of xyz being equal to 2x squared plus 2y squared minus z squared. And the hyperbolic paraboloid z is equal to z is equal to 3x squared minus y squared, okay? So again, find the vector, so just the vector, not the equation of the line this time, find the vector that is tangent to the curve of intersection between the level surface S, so let's call this S, right? The level surface S defined by this function, and the paraboloid at the point P1, 1, 2. Okay, so let us right here is the level surface. Right here we have a cone, right? And then we define, so we define the function, we define the function g. So I have f being 2x squared plus 2y squared minus z squared, and then g is equal to 3x squared minus y squared minus z, just by bringing z on this side of the equation, right? Okay, so if I plot the other surface right here, x squared plus y squared minus z squared is equal to 0, I get the hyperbolic paraboloid, okay? And then I have to find, let me just check something. I have to find the, where is the point A? Right here. I have to find the vector that it's tangent to this point, okay? So again, that vector is just going to be a cross product. So I need to find this vector right here, the vector tangent to the curve of intersection, okay, at the point A. But that one is going to be nothing else but the cross product of the gradient vectors, right? So these are there are the two gradient vectors. If I just make this a little bit more clear, we have gradient G and gradient F, okay? And as you can see, the vector that we are looking for, okay, is going to be orthogonal to both of them. So how do we find orthogonal vector to both of them? We find the cross product. So why don't we just do that? Let's find gradient f evaluated at 0.112. That's equal to, with respect to x, that's 4x. With respect to y, it's 4y. With respect to z is negative 2z. Evaluated at 0.112, I get 4 negative 4. And then gradient g evaluated at 1, 1, 2 is equal to 6x minus 2y minus 1. The derivative of g with respect to z is negative 1. Evaluated at 0.112, I get 6, negative 2, negative 1. Okay? Since I'm looking for a vector that is going to be orthogonal to both of these, right? I can take any constant multiple of either this vector or this vector. So basically what I'm saying, to simplify your calculation for grad f, you want the direction of gradient f, right? For this particular problem. So you might just as well take the vector 1, 1, negative 1. Why? Because it's parallel in the same direction with gradient f. So we have gradient f cross product gradient g is equal to ijk. So the cross product 4, 4, negative 4, 6, negative 2, negative 1. And that gives me the vector 12, 20, and 32. So that's how we get That's how we get the vector, this one here, that is orthogonal to gradient G and gradient F. That is a vector, tangent vector to the curve of intersections of these two surfaces. Now somebody might say, well, can I just find the curve of intersection and then find the derivative and evaluate at point A? Yes, of course, but what would entail that? First of all, you have to parameterize this curve of intersection, which you're more than welcome. You're more than welcome to do it. You're invited to do it, and you'll see that it's a little bit tricky. You don't know whether you should parameterize in terms of theta or in terms of r, and so on and so on, and then start finding the derivative, okay, with respect to the parameter that you decided to parameterize that curve. And just by looking at the gradient vectors, this boils down to what? Finding two partial derivatives and a cross product. So by using the gradients, this problem is way, way easier, okay? And I'll do one more problem here, one simple problem, saying, show that the ellipsoid 3x squared plus 2y squared plus z squared is equal to 9, and the sphere given by x squared plus y squared plus z squared minus 8x plus 8 minus 6y minus 8z plus 24 are tangent to each other at this point, okay? So I'll let you copy this problem while I open okay, so when we say that two surfaces are tangent to each other, okay, that means that they touch each other at this particular point, or in other words, they share a common plane. So what do we have? We have the ellipsoid right here, okay, 3x squared plus 2y plus z squared is equal to 9. And I have the sphere right here, okay? And of course the point A, which is the point where these two surfaces touch. They touch each other, right? Right here at this point. What do I know? Well, I know how to find the gradient vector at the point A of the ellipsoid, and I know how to find the gradient of, where is it? I just got confused a little bit. Okay, there you go. And I know how to find the gradient of the sphere at the point A also, right? So as long as I show that these two vectors lie on the same line, basically I'm done, okay? So let's see that. So I'm going to define f of x, y, z being equal to 3x squared plus 2y squared plus z squared is equal to 9. Gradient f is equal to 6x 4y 2z, evaluated at the given point, that's equal to 6, 4, 4, right? And then I will define the function g of x, y, z is equal x squared plus y squared plus z squared minus 8x minus 6y minus 8z plus 24 is equal to 0. and gradient g is 2x minus 8. Okay, the y component is 2y minus 6, and the z component is 2z minus 8. Evaluated the point 1, 1, 2, I get 2 minus 8 is negative 6, 2 minus 6 is negative 4, and 2 times 2 is 4 minus 8 is negative 4, right? And obviously these two vectors lie on the same line, right? They point at the opposite direction, okay? But also what you can do is that you can show that the tangent plane between these two, you can show that the tangent plane of both surfaces at the point A is just one plane. They share a common tangent plane. Not that you have to do that, but let's just show that. Let's just be aware, okay? So the tangent plane, I know that this is the normal vector to the tangent plane. So the normal vector times r minus r naught is equal to 0, the equation of a tangent plane. The normal vector is being given by the gradient. And because I just need the direction, let's say I'm going to take 3, 2, 2, right? Dot product x minus 1, y minus 1, z minus 2 is equal to 0. So that's 3x minus 3 plus 2y minus 2, right? I'm looking for the dot product, plus 2z minus 4 is equal to 0, or 3x plus 2y, 3x plus 2y plus 2z is equal to, this is 5 plus 4 is 9, is equal to 9, okay? And then you can see that you will get absolutely the same plane if you evaluate this one right here. Okay, so if you have this, let's say this is n1 and 2, dot product r minus r naught is equal to 0, negative 3, negative 2, and negative 2 times x minus 1 y minus 1 z minus 2 is equal to 0, so negative 3x plus 3 minus 2y plus 2 minus 2z plus 4 is equal to 0. 3 plus 2 plus 4 it's 9, and then bring the variables on the other side, you get absolutely the same plane, right? And of course, if we just plot this plane, we're going to be finally aware of what's going on. So 3x plus 2y plus 2z is equal to 9, and it's right there. The plane being, at least we can notice that this is not the tangent plane because it crosses the ellipsoid, and the mistake is right here. It's 2y, okay? And now we can see that the tangent plane, there is only one tangent plane at that point. They share a common tangent plane, which means that these two surfaces are tangents to each other at the point 1, 1.